So in this video we'll look at section 7.9 and the effect of pH on acid and conjugate base concentrations. So we'll begin with 7.91. It says that ammonium ion NH4 pKa equals 9.25 reacts with water to produce ammonia and hydronium ion. That would be NH4 plus H2O yields NH3 plus H3O plus. Then part A asks, at pH 9.25, which of the following is true? So we have the concentration of NH4 plus equals NH3 we have NH4 plus being greater than the concentration of NH3, or NH4 plus being less than the concentration of NH3. So which of these conditions is true at pH 9.25? Well, at that condition, pH equals 9.25, which equals the pKa. And so at the pKa, our acid and conjugate base concentration will be equal. And so this is our true condition. NH4 plus equals NH3. So at pH 5.25, we'll write that down. pH equals 5.25. Which of the following is true? Again, our choices are NH4 plus equals NH3 plus, NH4 plus being greater than NH3. There's no plus here. NH3 is a neutral molecule. All right. NH4 plus less than NH3. So at a pH of 5.25, our pH will be less than the pKa, because the pKa is 9.25. So we have essentially our conditions are more acidic than our pKa, and so that will drive the equilibrium towards our conjugate acid. And so this will be the true condition. We will have more of this NH4 plus than we will NH3. And choice C, or problem C, pH equals 13.25. Which of the following is true? Our three choices again: NH4 plus equals NH3, NH4 plus greater than NH3, NH4 plus less than NH3. Well, now we have a condition where pH is greater than pKa, and so this solution is essentially more basic than the pKa, and so that's going to push our equilibrium towards the right, and we'll have, helps if I show it, we'll have more NH3 than we will NH4, and so this will be our true condition. NH4 plus will be less than NH3. So 7.92 lactic acid and it gives the formula for lactic acid CH3 CH OH CO2 H has a pKa of 3.85 and it reacts with water to produce lactate. And rather than writing out lactic acid or the formula for lactic acid every time, I will simply say La, lactic acid, plus H2O yields La minus plus H3O plus. And this La minus would be our lactate. And La is lactic acid. So remember our pK is 3.85. Problem A, pH equals 3.85. Lactic acid, and our three choices are lactic acid equals lactate, lactic acid greater than lactate, lactic acid less than lactate. And this is a condition where our pH equals our pKa, and so at that condition our lactic acid and our lactate will be the same. So this is our true condition. Then problem B, we have pH equals 11.61. Again, lactic acid could be equal to lactate. Lactic acid could be greater than lactate. Lactic acid could be less than lactate. But when our pH is greater than our pKa, conditions are more basic, and so they would favor the formation of lactate, and so this will be our true condition. We will have more lactate than we will lactic acid. For choice or problem C, pH equals 1.66, and our choices are equal concentrations or greater concentration of lactic acid over lactate, or a lower concentration of lactic acid over lactate. And here we have pH less than pKa, so conditions are more acidic. I didn't draw any of that or show any of that. Anyway, conditions are more acidic, and that will push the equilibrium towards the lactic acid. Oh, nope. And so this is our true condition. Lactic acid will be greater than lactate concentration. So 7.93, part A. Again, pKa of NH4 plus equals 9.25. For the reaction in problem 7.71, what is there more of at pH 7.0? what is there more of? NH4 plus or NH3. And again, at when our pH is below our pKa, there will be more of our conjugate acid than there will be our conjugate base. And so there will be more of the NH4 plus than there will be NH3. For B, pKa of hydrogen phosphate, HPO42 minus, is 7.21. For the reaction in problem 7.71b, what is there more of at pH 10? So at pH equals 10, what is there more of? The hydrogen phosphate or phosphate ion. And now we have a pH higher than our pKa, and so these are going to be more basic conditions, and that will favor the formation of the phosphate ion, so there'll be more phosphate ion, more PO43 minus than there will be hydrogen phosphate. So 7.94. The Ka of methyl ammonium is 2.4 times 10 to the negative 11th. What is there more of at pH equal to 7.0? Well, the first thing I want to do is convert this Ka to pKa, simply because pKa's are easier to work with. So pKa equals negative log of 2.4 times 10 to the negative 11th. Negative log 2.4 e negative 11. Come up with a pKa of 10.6. So at a pH of 7, we're below 10.6. So there will be more of our conjugate acid, NH3 plus. And that would be, this is for part A. Part B looks at bicarbonate. It says Ka of HCO3 minus equals 5.6 times 10 to the negative 11th. For the reaction in problem 7.72b, what is there more of at pH 3.0? So the first thing I want to do again is find the pKa. It's negative log of 5.6 times 10 to the negative 11. Negative log 5.6 e negative 11. Come up with 10 point, let's just call it 10.3. pH of 3 below 10.3. There's going to be more bicarbonate than there will be carbonate. I'm getting bicarbonate and carbonate confused. There will be more HCO3 minus, more of our conjugate acid than there will be of our conjugate base. 7.95. Here we have to look at an amino acid and determine how its structure will be at different pHs. So at low pH, the amino acid aspartic acid has the structure shown below. So I will draw that out. H3N plus okay. So we have two carboxylic acid groups and an ammonium group. And everything is protonated. So we have hydrogens on our carboxylic acids and an extra hydrogen on our amine, so it has a positive charge. So part A, redraw aspartic acid showing the acidic CO2H and NH3 plus functional groups in their conjugate base form. So essentially, it's asking us to draw this at high pH. So we've stripped off all of these acidic protons, and this H3N plus becomes H2N, and our carboxylic acids have their protons removed, so now we have negative charges on those oxygens. Part B. In amino acids, CO2H groups have pKa's in the range of 1.8 to 4.3. And NH3 plus groups have pKa between 9.1 and 12.5. Draw aspartic acid as it would appear at pH 7. What is the net charge on aspartic acid at this pH? So at pH 7, we're going to have something in between the low pH form and the high pH form, because these different groups have different pKa's. And so this group here, this ammonia group, has a pKa of, let's just call it 10, in between 9 and 12. And this carboxylic acids will have a pKa, let's call it 3, because it's in between 1.8 and 4.3. And so when we're at a pH of 7, this pH of 7 is below 10, and so this will still be protonated, but it's above 3, and so these will not be protonated. So we still have our 3 protons and our positive charge on that nitrogen, but a negative charge on each carboxylic acid. And so what is the overall charge of this molecule? -1, because we have 1 positive and 2 negatives. So 7.96 asks us to do the same thing with the amino acid lysine. So it gives us the structure at low pH. And that's H3N. And we have 4 CH2 groups, 1, 2, 3, 4, and another NH3 group. So everything is protonated at a low pH. So we have 2 positively charged ammonium groups and a protonated carboxylic acid. So part A, redraw lysine showing the acidic carboxylic acid and ammonium functional groups in their conjugate base form. So we're drawing that at high pH, the H2N. Nope. We're deprotonating that carboxylic acid now. So that's a negative charge, not a proton. 1, 2, 3, 4. And this would be NH2. So both of our ammonia groups are NH2 instead of NH3+. Our carboxylic acid has this proton removed and replaced with a negative charge. And so, again, we have to draw the structure of lysine at pH 7. So at pH equals 7, again, that is below the pKa of our ammonia groups, and so these ammonia groups will be protonated at pH 7, so they'll be positively charged, but it's above the pKa of our carboxylic acid group, and so this will be deprotonated and become negatively charged. So we'll draw that out. One, two, three, four. So we have 2 positive charges, 1 negative charge. Overall charge equals positive 1 because of the 2 positives, 1 negative. So 7.97. An equilibrium mixture of carbonic acid, H2CO3, and bicarbonate, HCO3-, has a pH of 6.5. What happens to the carbonic acid and bicarbonate concentrations when the pH of the solution is adjusted to 8.5? All right, so we're taking the pH and we're moving it to more basic conditions. In fact, we're moving it to 100 times more basic. That's 2 pH units, and so 10 to the second is 100. As we make it more basic, our concentration of carbonic acid will decrease. Concentration of bicarbonate will increase because we're going from a more acidic solution to a more basic solution. And so we're going to increase the concentration of our conjugate base. (7.98), an equilibrium mixture of acetic acid, CH3CO2H, and acetate, CH3CO2-, has a pH of 4.8. What happens to the acetic acid and acetate concentrations when the pH of the solution is adjusted to 2.8? So now we're taking this solution, it's already acidic, it's 4.8, and we're making it more acidic, 100 times more acidic by pushing the pH down to 2.8. And so as we make this solution more acidic, our acetic acid concentration, CH3CO2H, will increase, and our acetate concentration will decrease because we're pushing the equilibrium towards the acid. And so that is it for section 7.9.